During that time, what you should use? You should use CO2 as the shielding gas, right? CO2 as shielding gas, right? Now, the advantages of being higher welding speed or greater penetration and lower cost also. So these are my advantages when I use CO2 as my shielding gas, right? Now, CO2 shielding produces high level of spatter, and during that time relatively low voltage is used to maintain a short burette kind of arc to minimize spatter, right? Now I have talked about these modes of metal transfer also. So we have talked about this globular transfer, then spray transfer, then short circuit transfer, right? Now uh, let us discuss a little bit again in terms of those globular, in terms of those metal transfer, right? Modes of metal transfer, because those are important parts or important aspects in your gas metal arc welding. Now here, how can we characterize a globular transfer, or how does it look like? So in globular transfer, discrete metal drops close to or larger than your electrode dia that travel across your arc gap under the influence of gravity, right? So it will look something like this. Let me take this again. What is happening? Huh. So it will look something like this. It's initially I will having this is my electrode, my globules are forming, then there will be making something like this, and my area will be much more less, right? And then there will be detachment of my globules. So that's how it will happen. And this figure is basically showing my globular transfer during gas metal arc welding at some specific current and with some specific shielding. As let us say we are using some argon shielding, to be in a stage of what shielding we are using. Uh, we are using argon shielding. We are using some 180 200 amp for this welding. So I'm giving some absolute value of my welding current. So globular transfer often is not smooth and it produces spatter. It always produces spatter. So at relatively low welding current, uh, globular transfer occurs regardless of the type of your shielding gas. So whatever shielding gas you will use, no matter what shielding gas you are using, globular transfer occurs relatively at low welding current, right? Now, with carbon dioxide and helium, however, it occurs at all usable welding currents. So, if you are using CO2 or helium or helium as shielding gas, globular transfer occurs at all welding currents. Otherwise, it will be generally at lower welding current, right? So keep that in mind. And as I already mentioned, a short Garrett arc is used in CO2 shielding gas metal arc welding of carbon and low alloy steel to minimize your spatter, right? So this is how it will look like in globular transfer. Now, how will it look like in spray transfer or when spray transfer occurs? So above a critical current level, there will be small discrete metal drop which travel across the arc gap under the influence of what? Under the influence of electromagnetic force, right? So there will be creation of electromagnetic force at much higher frequency and speed than in the globular mode. So how does it look like? My globular kind of metal transfer, it will look something like, so if this is my electrode, there will be some droplets of small droplets formation at certain level of welding current, right? So above a critical current level, these small discrete metal drops will travel across that arc gap under the influence of electromagnetic force, right? Uh, this is showing this figure. This figure is showing this spray transfer, and as I was saying, it has to happen above a certain level of ampere. So initially, I was talking about this 180 to 200, let's say 180 to 200 ampere of current. So it must have been greater than that. So it should have been something around 300 or 350 amp for this spray transfer. And let us say the shielding gas is similar, like the way I was using argon for the globular transfer one, right? Now over here, during this spray metal transfer, during this just wait, during this spray metal transfer, um, my metal transfer will be much more stable and it will be spatter free, right? So that is the basic difference of your globular transfer kind of metal transfer and in your spray transfer. So spray transfer is much more stable and it is spatterless. There will be no spatter formation when you are doing spray transfer at certain level of welding current, right? Now, your critical current level, what does it depend upon? So the my critical current level depends on the material what I am welding, or the size of the electrode, or the composition of the shielding gas, right? So those will be my factors where those will be my factors which will yeah. So those will be my factors upon which my critical current level will depend upon, right? And apart from this spray transfer and globular transfer, what else we have? What else we have discussed? Or uh, so there is something called short circuit transfer, right? So we have talked about globular transfer. We have talked about spray transfer. This I already have covered. Still I am discussing these parts because this will be a this will be a important aspect in your metal unit gas welding, right? So short circuiting transfer. So what happens in short circuit transfer? In short circuit transfer, the molten metal at the electrode tip is transferred from the electrode to the weld pool when it touches the pool surface, right? It has to have to touch the pool surface, and whenever it will touch the surface, there will be short circuiting, right? And short circuiting transfer encompasses the lowest range of welding currents and electrode dia. It produces a small, very small and fast freezing weld pool, right? These are we have already talked about. So we have uh, how can we characterize short circuit transfer? There will be a small and fast freezing weld pool. And when do you require a fast freezing weld pool or a small weld pool? When you want to join thin sections, right? So thin sections are joined with short circuit transfer. Right? Or what else? If you want to join some out of position welding, right? Such as you can do some overhead position welding, or you can do some bridging large root openings. So those are few examples when you should go for this short circuit transfer, right? Now, so so we have talked about this schematic of gas metal arc welding setup. Now, how my welding torch will look like, or what kind of welding torches are used in gas metal arc welding, right? So we saw that we have to use some kind of welding torch, right? What does welding torch do? Basically, it energizes your electrode, right? Or it feeds the electrode and the shielding gas. That's what it does, my welding torch, right? So there can be either air cooled or water cooled welding torch, right? Whenever your torch will be working above some 200 amp or above that, right? So my torch have to have some kind of cooling aspect. So welding torch need to be air cooled or water cooled. Is it not? So what are three different main types of MIG welding torches what you have covered in your earlier lecture? What are those? So we have push type welding torch, we have pull type welding torch, and we also have a push pull type welding torch, right? So there are mainly three different types of welding torch. One is push type, one is pull type, and another is push pull type. Now, in terms of principle of how you should initiate these arcs, these are all similar to what you do during a shielded metal arc welding, right? So basically, over here the difference is before ignition of your arc, your gas and water should be checked that it is in a proper condition or not. Then proper current and where speed should be set, and your electrical connection should be ensured. And as we say that your arc should be struck by any of the two methods. So what are those two methods? These we have already covered in your TIG operation also. So in the first method, you can switch on your current and shielding gas, and you can scratch your electrode material against the workpiece as the usual practice. What do you do for shielded metal arc welding? For striking the arc, right? And what the second method is, in the second method, your electrode, you touch the electrode with the workpiece and then you retract or withdraw and then move forward to carry out the welding, right? So those are two different methods or two different practices of doing welding. You know? Now this is my principle of how should I initiate my arc. Now in terms of different kinds of arc we generate in between this electrode and workpiece, what kind of arcs you can generate? So you can generate or you can form two different kinds of arcs, right? So one we call self self-adjusted arc, another is called what? Self-regulated arc, right? Another is called self-adjusted or self-controlled arc, right? Now in self-adjusted arc, so basically how do you control my arc length? How do I control my arc length uh, by using this wear feed mechanism, you know? So in your self-adjusted arc, my electrode is fed from a coil which will be run by some roller at a constant speed motor. So in my self-adjusted arc, it will be a constant speed motor, correct? Now for the self-adjusting arc, um, a welding power source with flat characteristics is always preferred over these drooping characteristics, right? Why? Now there is some reason why require these flat characteristics during this uh, self-adjusted arc. So in my self-adjusted arc, let's say, let me draw this. So let's say this is voltage and this is current, and let's say this is having a flat characteristics of power source, and I'm having two voltage current characteristics of two different arc length. Let's say this is for arc length L1 and this is for arc length L2, where L2 will be greater than L1, right? Now, with the same change in arc length, if I having same change in arc length, what is happening? If there is any same change in arc length, there will be a bigger change in my arc current with flat characteristics, right? If there is any bigger change in your arc current with flat characteristics, it will increase or decrease the electrode burn off rate. So in self-adjusted arc, um, sorry for my tablet is not working, but anyhow, it's taking time actually. So for self-adjusted arc, um, electrode burn off rate is getting controlled.